We will see the preparatory methods. First type is from unsaturated hydrocarbons. We know unsaturated hydrocarbons are alkenes and alkynes. So from alkenes and alkynes we can prepare alkanes. It is due to this process is known as catalytic hydrogenation, that is addition of hydrogen. In this process, dihydrogen is passed through the alkenes or alkynes in the presence of finely divided catalysts such as Rani nickel, platinum or palladium. In this reaction, these metals absorb dihydrogen gas on their surfaces and activate the hydrogen-hydrogen bond. So we require high amount of energy for this reaction. For example, CH2 double bond CH2, we are adding dihydrogen in the presence of either platinum, palladium or Rani nickel. We will get alkynes. So from unsaturated we are getting saturated compounds. Then from alkyl halides, except fluoride, but from all other halides we can prepare alkynes. That is, this is one of haloalkane, that is alkanes which contain either chlorine, bromine, iodine. These compounds are known as alkyl halides. By adding hydrogen, we will get, in the presence of zinc, we will get our alkane. Here in H2, the HCl will remove from the compound and another hydrogen will add to the compound. Such type of reaction we can see. From that alkyl halides we can prepare our hydrocarbon alkynes. And another reaction is alkyl halides are reacted with the sodium metal also will get alkanes. And this reaction is known as Wood's reaction. That is, alkyl halides on treatment with sodium metal in dry ether solution give higher alkynes. This reaction is known as Wood's reaction and is used for the preparation of higher alkanes. Here only contain one carbon, but the alkane which getting 2 carbon. So from the reagent which carrying 1 carbon to reagent which carrying 2 carbon. So it is the method to prepare higher alkanes. We will see from carboxylic acid. From carboxylic acid there are 2 methods. First one is decarboxylation reaction and next one is Kolb's electrolytic method. We will see what is decarboxylation. Sodium salts of carboxylic acid on heating with soda lime. Soda lime is mixture of sodium hydroxide and calcium oxide. Gives alkanes contain 1 carbon atom less than the carboxylic acid. This process is known as decarboxylation. Here carboxyl group is reduced to carbon dioxide. For example, it is the sodium salt of carboxylic acid. That is, instead of CH, we know carboxylic acid have the functional group CH3COOH. In here, H is replaced by any other metal. For example, sodium, that is sodium salt, which reacted with the sodium hydroxide in the presence of calcium oxide will get the alkane which having less number of carbon atoms. As here you can see in this compound 2 carbon atoms are there, but here after the reaction we are getting the alkane which carry 1 carbon atom. This method is known as decarboxylation method. Next method is Kolb's electrolytic method. Here in aqueous solution of sodium or potassium salt of a carboxylic acid on electrolysis gives alkane contain even number of carbon. For example, it's sodium acetate, that is sodium salt of carboxylic acid. We are hydrolysing and we are conducting electrolysis, that is we are passing electricity through this. So you get alkynes. The mechanism is here. That the anode acetate ion will be there and it is will form to acetate free radical, methyl free radical. This is the reaction occurs in the anode. This is the reaction occurs in the cathode. In the cathode, you can see this reaction. We'll see the properties of alkynes, the physical properties and chemical properties. What are the physical properties of alkynes? Alkynes are almost non-polar molecule and they are non-polar and they contain weak van der Waals forces. These weak forces depend upon only the size and the structure of the molecule. And lower members of these alkanes are gases, and next 13 alkanes, that is lower members from C1 to C4 are gases, from C5 to C17 that are liquids, and higher members are solids. And if you check with the boiling point, alkanes have generally low boiling point because they are non-polar, and we know it's held together by weak van der Waals forces. So in order to break this weak van der Waals force, we require only less energy. So with the increase in the number of carbon atoms, the molecular size increases and therefore the magnitude of van der Waals force also increases. So the lower members having low melting point, but the high members having high melting and boiling point. So the boiling point and melting point increases with increase in the number of carbon. Here you can see the trend. If number of carbon atoms increases, the boiling point also increases. Next one is melting point. Melting point of alkanes do not show a regular variation with the size. It has been observed that in general, the alkanes with even number of carbon atoms having higher melting point as compared to the immediately next lower alkanes with odd number of carbon atoms. So even number carbon containing compounds having high melting point. It is because the alkanes with even number of carbon atoms having more symmetrical structure rather than the odd number containing alkynes. If there is a symmetrical structure, the melting point will be increases. Solubility. Alkynes being non-polar in nature, so they are expected to be insoluble in water. They are not soluble in water, they are dissolved in non-polar solvents such as ether, benzene, carbon tetrachloride. These all are non-polar solvents. So the alkanes are soluble in non-polar solvents. So generally the solubility decreases with increase in the molecular mass. Density. Alkanes are lighter than water. The density increases with the increase in the number of carbon atoms. We'll see the chemical properties, what type of reaction they will undergo. First type is substitution reaction. We know what is substitution reaction. The reaction in which an atom or a group of atoms in a molecule is replaced by some other atom or a group of the atom. That is in the football and all, we know the substitute players. If one main player will go, a new substitute player will come. Similar to this, an atom or molecule in the compound is replaced by some other atom or group of atom. Alkynes undergo substitution reaction which one or more hydrogen atoms are replaced or substituted by different atoms or groups such as halogens, nitro group or sulfonic group. We know in hydrocarbons it contains only carbon and hydrogen. So one of the hydrogen is replaced by either halogens or nitro group or sulfonyl group. We'll see halogenation. It involves the replacement of one or more hydrogen by halogens. So in the reaction, order will be like this. Fluorine will be most reactive and iodine will be the least reactive. So CH4, methane is reacted with chlorine, will get CH3Cl. One of the hydrogen from methane is replaced, and here 4 hydrogens are here after the reaction 3. Here you can see some other examples. And the mechanism: initiation, propagation. Initiation, that is the reaction initiated by homolysis of chlorine. That is, first step, the chlorine will break into chlorine free radical in the presence of light. Next one is propagation, that is our methane reacted with the free radical formed here will get methane free radical. That's methane free radical will react with again one more chlorine and it will give free radicals. Last step is termination. These free radicals will combine together and we will get the compounds. Next type of reaction is combustion. Combustion is the burning or heating in the presence of oxygen. This is known as combustion. So the compound is completely oxidized to carbon dioxide and water with devolution of large amount of heat. If methane is heated in the presence of oxygen, we will get it is decomposed to carbon dioxide and water and it will produce high amount of heat. Next one is controlled oxidation. Alkynes on heating with a regulated supply of dioxygen or air at the room temperature in the presence of suitable catalyst, we will get different types of oxidation products. The products will get up to it will depend upon the reagent we are using. When a mixture of methane and oxygen in the molar ratio 9:1 is compressed about 1100 atm, that is pressure, passed through copper tubes at 575 Kelvin, we will get methane oxidized to methanol. So if you are using these conditions, that is atmosphere pressure should be 1100, we should supply 575 Kelvin, the reagent is copper tubes, will get methanes, will get alcohols, that is C2, will get methanol, so CH3OH. From CH4 we will get CH3OH. The next type, when methane is mixed with oxygen and passed through heated molybdenum oxide under pressure, will get methanol, that is our methane is converted to aldehyde. Then we will see isomerization. We have seen what are isomerization. Here the butane is reacted with anhydrous AlCl3, will get isopropane. That is the straight chain converted to branched compounds when heated with AlCl3 and hydrogen chloride in the presence of high pressure and temperature. Sometimes it will form benzene ring. Open chain structure also give benzene ring when applying this type of energy. Reaction of steam. On passing mixture of steam and methane over heated nickel, these are our catalysts, at high temperature, methane is oxidized to carbon monoxide and hydrogen. This pyrolysis portion is deleted. This is no need to study pyrolysis, it is in the deleted portion. And we will see the conformation in the next class.